Hello again. This is another part for chapter 3 I'm going to cover, and hope you're doing well. Let us get started on that. So we are going to talk about derivative of trigonometric functions. Last time we looked at some applications of derivative, and now we want to talk about trigonometric functions. So first of all, we used this animation before, and that was creating the derivative function using the slopes of the secant lines, right? Remember? So what we can do is we can change the function in here. See this change of this function, I'm going to make it maybe sine x. And now, so what I'm going to do is I'm going to move this point, right, and see this is the function sine x. So I'm going to change the different values here, and at every value we are going to have a slope of the secant. So the calculator is going to calculate the secant line from here to a point really close to it, about 0.1 unit to the right of it. And at every given point, as you see, I'm creating those points which give the slope of the tangent line at that point. For example, right here, the slope of not the tangent line, but the secant line. So the slope of the secant line at this point, if I go to the right of it about 0.1 unit, would be that much from here to here. You see, is the y coordinate of that red dot right there. And as you see, if I go through this sine, few cycles of the sine, we see what the derivative of sine is. What does it look like? Well, it looks like a cosine function. You see that? It looks like cosine. So we can say derivative of sine is probably just cosine, right? Of course, that's not proving it that way, right? But we can say that. Also, if I get rid of that and get rid of the red points and change it to cosine x, right? And then now do the same thing. Create those slopes of the tangent lines, right? What does it look like now? So the red points are going over basically a pattern, and that pattern is a function itself, and that's the derivative function. So derivative of cosine, which is the green function, is the red function. And the red function looks like sine function that is flipped, right? So that's sine function flipped. Sine function is supposed to be right here, right? So it's sine function, but it's flipped. That means it's negative sine. So that's our observation here. So let's go and actually prove that this is actually the fact. So we're going to prove just the sine, and then we go from there. The rest of them are, cosine is similar, and the rest of them are related to sine and cosine. So let's do that. So derivative of sine, how do we find derivative of sine? We have to set up a limit. So what's the derivative of sine at a given point x? Well, if f of x plus h minus f of x over h, and then let h go to 0, right? So we get this. Now we have to simplify this. Remember, in this kind of limit, we can never substitute and find the limit, because the trouble is built into this. We always get what? 0 over 0 if we substitute. So we got to get rid of that h, but this is different because it's not a polynomial. I can factor it and get the h out of it. It's trigonometric function. So we have to rely on trigonometric identities. Here is the one that is useful here. So sine of a plus b is sine of a times cosine b plus cosine a times sine b. That's trigonometric identity from trigonometry. You learn that in pre-cal or in trigonometry. Now we're going to use it. So this part right here, we're going to use this to break it down into sines and cosines, right? Right here. And then minus sign is still there, right? So this part becomes that, and then minus sign. Now we can take the sine here, right? If you leave the cosine alone, right? Cosine times sine, you leave this alone, and take these two and factor the sine out of it, we get sine times cosine h minus 1, right? And leave this alone. All right, now we are going to separate this into sine x times this part over h, and then this part over h, right? H is a common denominator. Now, you've seen this structure before, right? Remember the structure? We proved that already. There was a special limit in the other chapter, chapter 2. So we know this limit equals to 0, and we know this limit was a special limit and equals to 1 when h approaches 0, right? So that means in this structure here, this part, the limit of this part, would be 0, right? And so this is 0 times sine x, it gets rid of that, so that's 0. And this part is nothing but cosine times sine over h, and sine over h is the limit is 1. So this goes to 1, so 1 times cosine is cosine. So the limit is cosine x. That means the derivative of sine is cosine. All right? That's the idea. That's how we prove it. The cosine is proved the same kind of way, similar, and you have to use trigonometric identity to prove it. So I'm going to show you the formulas already. You kind of have to memorize these. Gradually, when you do practice, of course, with problems, you are going to memorize these, but a calculus student should know the derivative of all 6 trigonometric functions. So derivative of sine is cosine, and derivative of tangent is secant squared. Derivative of secant is secant tangent. We can prove all of these, and we're going to do that using the quotient rule. So cosine, cotangent, and cosecant, you see there is a pattern. Derivative of the functions that have co-functions, they're all negative. So derivative of sine is cosine, and derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. Derivative of secant is secant tangent. Derivative of cosecant is negative cosecant cotangent. Again, you gotta have to gradually memorize these, okay? So let's look at an example. What's this derivative? Well, this is a difference of 2 functions, and this is a product of 2 functions, so we can take the derivative. So derivative would be, well, derivative of x is just 1, right? That's given. So this first part is just 1. Now this one, we can think of it as u times v, and we know the derivative of uv, right? Derivative of uv is u prime v plus uv prime. So let's do this part separately. That's easy. That's just 1 minus whatever we get here. So what do we get there? Well, let's see. U prime is 3x squared times v, which is sine x, plus u times derivative of v. Derivative of v, we just discussed that. Derivative of sine is cosine. And that, we are done with this part. Now, so derivative of this given y, dy dx, is derivative of this, and derivative of x is 1, and derivative of this part we just found, right? And we just write it as one expression. So this is derivative of that. All right. All right. So what's derivative of tangent? What is secant squared? Can we prove it? Yes. You just have to write what? You have to write tangent as sine over cosine, and then use quotient rule. So this is u over v, so that's u prime v, right, minus u v prime. But if u is sine, then derivative of u is cosine, and then v is cosine, so it's cosine cosine, plus minus, right, there is a minus here, u, which is sine, so minus sine x, times derivative of cosine, which is negative sine. So that's why we have a plus here, because negative times a negative is positive. And the denominator would be cosine squared. All right? All right, now, so derivative would be basically cosine squared plus sine squared here, right? And we know that's an identity. Cosine squared plus sine squared is 1. 1 over cosine squared. And 1 over cosine squared is secant squared. So we prove it. We proved it. So derivative of tangent is secant squared. And what's the derivative of this? That's a product rule. Again, think of it as uv. And the answer would be derivative of uv prime. uv prime is u prime v plus uv prime. The prime of uv is u prime v plus uv prime. And u is sine, so u prime is cosine. V is tangent, we leave it there, plus u, which is sine, times v prime. Now v prime is derivative of tangent, which is secant squared. And now we can just, you can maybe simplify it and write it in different form. In trigonometry, usually if you write everything in terms of sine and cosine, you make it something simpler. But for now, that's good enough answer. All right. Can we prove that derivative of cotangent is negative cosecant squared? Yes. Write cotangent as cosine over sine. Again, is u over v, right? And derivative of u over v, of course, is u prime v minus uv prime over v squared. And if you substitute here the right expressions, you can easily prove it. So here goes u prime v. U is cosine, so u prime is negative sine x, times v, which is sine, minus u, which is cosine, v prime, which is derivative of sine, which is cosine, divided by v squared. Now, this is negative sine squared minus cosine squared, which is, if you factor the negative out, is negative cosine squared plus sine squared. And sine squared plus cosine squared is 1, so that's negative 1 over sine squared, which is negative cosecant squared. So that's the proof of it. All right? Now, can we prove that cosecant, derivative of cosecant is negative cosecant cotangent? Yes. So write cosecant as 1 over sine and use quotient rule. So we could use chain rule, but we haven't talked about chain rule yet. So we could use chain rule, actually. We did. We could, but we're going to use quotient rule. So 1 over sine x, right? So this is u, and this is v. So this would be, again, u prime v minus uv prime. So u prime is 0, because derivative of a constant is 0. V minus u, which is 1, derivative of v, which is cosine, over v squared. Now this goes away, so we just get negative cosine over sine squared. Is that the same as that? Yes. The trick is write sine squared as sine times sine. So if you write this as sine x times sine x, then you can separate, you can put these together, right, and then put 1 over sine separately, like separate the two fractions, and you get this. So that's cosecant, and cosine over sine is cotangent, and put the negative right before it, and that's the proof. All right, so can we prove that derivative of secant is secant tangent? Yes. Again, it's the same kind of procedure. Think of it as a quotient, and you can stop the video and see if you can follow this. I'm not going to explain it more because it's obvious, right? But you have to kind of maybe convince yourself that this is true. And so let's move on. If you stop the video and figured it out, let's move on. So a particle moves along a coordinate axis in such a way that its position at time t is given by this. For t between 0 and 2 pi. At what times is the particle at rest? So this is an application, of course, of derivative. Don't forget, we learn calculus, not for the sake of learning calculus. Of course, some do that, very few. But the whole point is to apply it. So let's look at this. How do we figure out when the particle is at rest? Well, particle is at rest if the velocity is 0, right? And we know what velocity is. Velocity is the prime of the position. So basically we have to take s prime, right, and set it equal to 0 and in this interval. Remember that trigonometric functions are periodic, so they go up and down, right? They're periodic and periodic functions. So when we want to work with them, you have to decide where, what part of the domain you're working, right? So that's what we have to do. So take the s prime. What's s prime? Well, derivative of 2 sine, you keep the 2 and take the derivative of sine, which is cosine. And then minus what's derivative of t? 1. So that's 2 cosine t minus 1, right? And s prime is 2 cosine t minus 1 equals to 0. So we set it equal to 0 to figure out what makes it 0. And we get the trig equation, trigonometric equation, right? And you know that on the unit circle, right, from 0 to 2 pi, if you go around one time, right, when is it that cosine is 1/2? Well, cosine 1/2 happens here, right? So either the angle has to be that one, cosine 1/2, or it has to be this one. So one time around is either this angle from here to here, or is this angle, right? And if you know your, cosine of what angle is 1/2, if you don't remember, of course, we can use a calculator, right? So let's see. Calculator should, I think I opened 2 calculators. Here you go. I closed one of them. So with the calculator, if you want to know in degrees the answer, you can go to mode and change it to degree. Of course, here we want to use radian, but the answer is nice if it's degrees, so we can convert it. So we change the mode to degree, and then we put what? We want to know what angle is it that has what? That's cosine is 1/2. That's inverse cosine, right? So we put inverse cosine of 1/2, 0.5, which is 60 degrees. So calculator doesn't give you both answers. It just gives you one of them. It gives you one of them. So the calculator gave us what? This one. Because calculator, remember, the cosine inverse, the restricted domain for cosine inverse is over here, from 0 to pi. So when you put cosine inverse of something in the calculator, calculator only looks in this region for an answer. Of course, it found that one. Now, we know that if this is 60 degrees, what's that big one? Well, we know if this is 60, this is symmetric, So this angle right here is negative 60 or 60 degrees. So how much do I have to go to get to this point? I have to go 360 minus what? 60. So that's 300 degrees. And we know that 60 degrees is like pi over 3. Think of pi as 180 degrees divided by 3 is 60. And 300 degrees is 5 of these, right? 5 60 degrees. So 5 pi over 3. So there are two angles where cosine is 0, from 0 to 2 pi. Pi over 3 and 5 pi over 3, right? So our answer to this question is that the particle is at rest at times t equal to pi over 3 and 5 pi over 3. All right, it says find the equation of the tangent line to this function at x equal to 0. Now we know equation of a tangent line in calculus is given by this formula here. Y minus f of a equals to f prime at a times x minus a. So in order to do this, we need a, which is given, 0. So a is 0. So that's 0, that's 0, that's 0, right? So we have to just find f of 0. Well, f of 0 is negative sine 0. Sine 0 is 0. So that's 0. So this value here is 0. So it's y minus 0, right? And now, what is f prime at 0? Well, we know f prime for this function. What's f prime? Well, f prime, we keep the negative. What's the prime of cosine? Is cosine. Remember, the negative was part of the function. So f prime is negative cosine. Now, what is f prime at 0? Is negative cosine 0. And that's negative 1. So what goes here is negative 1. What goes here is 0. What goes here is negative 1, and we are done, right? That's the equation. And the equation is right there. That's the equation of the tangent line to the graph of y equals to negative sine x at 0, right there. And again, calculators, computers can do all this for us. The question is here, the point here is to understand what that tangent line actually means at that point. And how to write these equations, right? That's what mathematics is all about nowadays in 21st century. It's not about, writing these things and figuring them out, because these procedures are programmed into machines, and the machines can do it for us. Calculus is not about procedural stuff. You got to know how to do it, but that's not why we learn calculus. Now, before technology, we needed people to actually do all of these calculations by hand. So people had to be really good at taking derivatives, figuring things out. But nowadays, you just have to understand the concepts. So it's a lucky time for you, right? So here's another one. F of x is secant. And if you're rusty on your trigonometry, you should review it. Again, chapter 1 has some trigonometric stuff to review. You can do that. And or you can go to the pre-calculus channel and pre-calculus playlist and watch the videos on pre-calculus stuff. Okay, so how do we do this? Again, the same setup, right? Y minus f of a equals to f prime of a times x minus a. Our a here is pi over 4. This right here, a is pi over 4, right? This is pi over 4 here, and this is pi over 4. So we're going to have to find f of pi over 4, which is secant of pi over 4. Now, secant pi over 4, remember, secant is 1 over cosine. So secant of pi over 4 is 1 over cosine of pi over 4. Well, what is cosine of pi over 4? This is square root of 2 over 2, right? So 1 over a number is a reciprocal. So that is what goes here. Not there, actually. That is what goes there, right? So y minus 2 over the square root of 2, that's that part, right? And then you can rationalize it by multiplying the square root of 2 over 2, right? That's just rationalizing it, but that's what goes there. So 2 over the square root of 2 is f of a. Now f prime, what's f prime? Well, f prime, you know the derivative of secant is, what's the derivative of secant? Well, the derivative of secant is secant tangent. And derivative at pi over 4 is going to be what? Is going to be secant pi over 4 times tangent pi over 4. Secant pi over 4 is 1 over cosine pi over 4, we know that. Tangent 45 degrees is 1. So, now you can use calculator if you're not sure about these values, but these are the angles that are commonly used in, at least in the examples used to teach these things. You should know those. All right, so f prime at pi over 4 is 2 over the square root of 2 again. So that means this part is also 2 over square root of 2. Right, here we go. Now we're done. That's it. This is our answer. We can simplify it. And you can stop the video and make sure you see how the answer went from here to there. That's just rationalizing and multiplying by things, right? So you can stop the video and go over that. And here's the picture of it. This is the graph of secant. This is the point pi over 4. Pi over 4, pi is 3.14 over 4 is a little bit less than 1. So that's the point pi over 4, about right there somewhere. So at that point, the slope of the tangent line is 2 over the square root of 2, and the equation of it is this right here, or that. All right. So higher order derivatives for trigonometric functions, these are pretty useful in calculus 2, because in calculus 2, we like to write functions in terms of polynomials, and to do that, you have to be able to take many derivatives of a same function. And that idea requires you to be able to find patterns in derivatives, and some functions have patterns like this. So if you think of sine x, what's the fifth derivative of sine x? Well, the first derivative is cosine, and the second derivative would be derivative of cosine, which is negative sine. Third derivative is derivative of this, which is negative cosine. The fourth derivative is negative sine, which is sine. So it looks like we went back to what? Where we started. So, so the first derivative is cosine. So if you think of this, the nth derivative of y, where y is sine x, the first derivative when n equals to 1 is cosine, when n equals to 2 is negative sine, 3 negative cosine, 4 sine. So the fifth derivative would be going back again to the first derivative. So it's just like you do all that and then you do it one more time. So it's like you start all over and just take one derivative, right? So if I want to find the fifth derivative, I go through this process for one time, this 4, the group of 4, and then I take one more. Now what if you want to take, let's say, seventh derivative? What if you want to take seventh derivative of sine x? Well, seventh derivative, think about it. If I divide 7 by 4, I get 1. And I mean, 1. What am I doing? 7 by, see, in high school I learned to put, since I didn't go to high school in the United States, so we put 7 outside, not inside. So we write it this way, but I have to do it this way here. So 1 times 4 is 4, and we get 3 here. So the remainder is 3. What does that mean? That means if I want to take 7th derivative, I have to go through this group 1 time, right? And then the remainder is 3. That means I start all over again and do 3 derivatives. 1, 2, 3. So the answer would be this one. Right? All right, so this way we could take any really higher derivative of sine. So what if you want to take 74th derivative of sine? Well, 74, when you divide 74, right, by 4, what do you get? You get 34, and then what's that? That's 8. So that's 32, and the remainder is 2. That means we have to go through this group of 4 how many times? 18 times. 1, 2, 3, 4, 5, 6, all the way to 18. And then do 2 more derivatives. So I get to this number. So 74th derivative of sine is just negative sine. It's just like you're doing 2 derivatives, right? And that's what you get. You get negative sine. All right? Again, this is important skill to have in calculus 2. All right, so I think I said we covered chain rule, but we didn't, obviously. And so we're going to do it now. Okay? That's why I couldn't use chain rule on that problem. All right. So chain rule. What's chain rule? Well, sometimes we have functions that are functions of other functions. Remember, we have this in algebra, f of g of x, right? Remember that? So we can think of this as a function, x squared plus 1, which is inside another function, which is something squared, right? Now, what if we have something like that? How do we take the derivative of something like that? Well, why don't we just use our power function and see what happens? So when we take derivative of x to n, right, what do? We do nx to n minus 1. Can we do this if x is actually a function, like here? Well, let's see. So what's the derivative of this if we use the, well, I give you, I'm going to spoil it for you. It's going to be wrong, but let's see. So what's the derivative? It's going to be 2 times x squared plus 1 to the power of 2 minus 1. So that's the answer. Is this really the answer for derivative of this? Well, let's see. Why don't we expand it, right? If we expand it, what do we get? We get this is squared, right? So expanded, we get x to the 4th plus 2 times this, 2x squared plus 1 squared. What's the derivative of this? Well, it's 4x to the 3rd plus 4x, which is not the same as what we got here. So that means don't use this formula if you have something like this, right? If there's a structure to the nth power, the derivative of it is not just n times that structure to n minus 1. We're going to see the answer is this, but you have to take the derivative of inside and multiply by that too. And that's what we're going to do. So derivative of a composite function is not this right here. You don't apply the formulas for composite functions. What do? Well, let's see. It looks like we are wrong by what? By a factor of 2x. And looks like that factor of 2x is derivative of inside function that we had to multiply by, right? So, so I give you the formula, and then we kind of try to prove it. So if you have a derivative of f of g of x, right? If you want to take derivative of f of g of x, you say the derivative is f prime of g of x multiplied by g prime of x. That's it. That's the formula. All right? So let's do an example also before we prove it. Let's do an example. Here you go. So suppose somebody tells us, what's the derivative of sine of x to the 3rd power, right? Well, we can't just use the formula, say, well, derivative of sine is cosine, so the answer is cosine x to the third. No. Here's how you argue here. You say derivative of sine of something is cosine something times derivative of something. Isn't that something? Now that was a joke. Of course, inside function, derivative of inside function, you multiply by and you're done. That's the formula. So derivative of sine x to the third would be cosine x to the third times what? 3x squared. Remember, 3x squared is not the argument of cosine. That's why we like to write it maybe before cosine, like this, right? We multiply by derivative of inside function. So that's the formula. So can we prove it? Yes, we can prove it this way. Let's do one more example with a new notation. So if y is a function of u and u is a function of x, then derivative of y with respect to u would be dy du, right? And derivative of u with respect to x would be du dx. What if you want dy dx? Well, dy dx would be that times that. So dy du times what? Du dx. Of course, here you get something in terms of u, and here you get something in terms of x, but the answer has to be in terms of x. So what you do, once you get this answer, you know what u is, right? You substitute whatever u is in terms of x here, and you have the answer. All right, so now don't cancel these. That's not how it works. But the answer is dy dx. Okay, so y equals to u squared plus 2 and u equals to x to the third. Find dy dx. So you see y is a function of u and u is a function of x. So we write it like that, and so the answer would be dy du. What's the derivative of this with respect to u? So u is the independent variable. Well, that would be 2u, and derivative of that is 0. And then times, what's the derivative of that with respect to x? Would be 3x squared. That's the answer, but the answer, notice, is not in terms of x, but it has to be in terms of x. So what we do is substitute for that u, which is x to the third. And the answer is 6x to the fifth power. Okay? And if we don't, so without the chain rule, we can say, okay, y equals to u squared plus 2, u is x to the third. So if you substitute x to the third here for u, we get x to the 6 plus 2, and then if you take the derivative, you get that. So the answer is correct. But we can't always do that. This would be really difficult to do, right? So we have to use chain rule. So how do we prove chain rule? Well, it's really not that hard to prove chain rule. So think of y as a function of u and u as a function of x. Now, delta y over delta u is the slope of the secant line, and this is the slope of a secant line. So when we multiply delta y over u times delta u over x, we are able to cancel these, because these are just values can be canceled, and you see that delta y over delta u times delta u over delta x equals to delta y over delta x. What we want to prove is that, is it true also for dy dx equals to dy du times du dx. That's what we want to prove. Now these values are not just numbers, these are limiting values, so we can't just cancel them and say, okay, the answer is that. No, that's not how it works. You have to prove it. Here we can start with this idea. This is true, okay? So let's start with that and take the limit of both sides when delta x goes to 0. So obviously the limit of that when delta x goes to 0 is dy dx, right? And the limit of that would be, well, the product of the limits, right? Limit of this times limit of that. Now we know what this is. This is u prime, right? This is du, or in terms of Leibniz notation would be du dx. That's by definition, that's correct. Now the point is this dy dx? We know it's dy du, but we want it to be dy du, I meant. Right? So we want it to be dy du. Is this dy du? We don't know, because we know delta x goes to 0. How do we know that delta u goes to 0? Now, if delta u goes to 0, we can say this is dy du, and we proved it. So the only thing that we have to do here, we have to prove that when delta x goes to 0, delta u goes to 0. And we're going to do it here. Now, the assumption here is that these functions are differentiable, right? Du is, u is a differentiable function. If the inside function is not differentiable, you're not going to be able to find the derivative, right? So du dx exists. Now, if this is differentiable, if u is differentiable with respect to x, then we know differentiability implies continuity. Remember, if a function is differentiable at a point, for sure it's continuous. But not the other way around. If it's continuous at a point, doesn't mean it's differentiable. But if it's differentiable, for sure it's continuous. So if this is continuous, if u is continuous, then u is continuous at a. A is a domain value of u, right? So when x approaches a, then delta x approaches 0, right? Because what is delta x? It's the difference between x and a, right? So now we know that the limit of u of x when x approaches a has to be u of a. Why? Because we know it's continuous, right? U is continuous, and that is the definition of continuity. So we know this is true, and we know this is true. Well then, what is u of x minus u of a? U of x goes to 0, right? Now, delta u is u of x minus u of a, right? If you have a function, this is a and this is x, this is u, then this would be u of a, and that would be u of x there, the y-coordinate of that. So u of x minus u of a, right, is going to be 0. Why? Because we know the limit of u of x when x approaches a is 0. I mean, is u of a. And then if you move this to this side, you see that delta u goes to 0. So we prove that when when delta x goes to 0, delta u goes to 0. So we prove right here, when this goes to 0, this goes to 0 too, and now we can say that if this goes to 0, that defines what? Dy du. And we prove that chain rule. All right, this is just one of the proofs of chain rule, and it's called proof via infinitesimals. There are many other ones. If you search and go to Wikipedia, you can find at least 3 or 4 more proofs. Okay, that's just probably the easiest one. All right, so let's use chain rule. So now using chain rule, we say, what's the derivative of something squared? Well, the derivative of something squared is 2 times something to the first power, right? And that something is x squared plus 1. That's that part of it. And then the formula says derivative of chain rule. Derivative of this is derivative of the outer function, which is something squared, times what? Derivative of inner function, which is 2x. And that's the answer, right? So, so the answer is basically 2x times what did I do here? Yeah, that's what it is. So the derivative is, I use u and separated this. You don't have to. You can think of this as y equals to u squared, and u equals to what? X squared plus 1. So if you want to find the derivative dy dx, you have to do what? You have to do dy du, which is 2u, and then times dy dx, du dx, which is 2x, right? And now what is u? U is x squared plus 1. If you substitute u for it, simplify, you get that. You don't have to go all that. To do all that, you could have just done what I did. What I said was, this is y equals to something squared, right? So what's the derivative of something squared? Is 2 times something to the first power, right? And then times the derivative of what? Inside, which is 2x. And if you multiply all that, you get this. All right, so chain rule is really easy to use if you think of it that way. Now, here is something useful to memorize. Derivative of the square root of something, let's put something like a triangle, is 1 over 2 square root of something times something prime by chain rule. So derivative of this is, what's the derivative of square root of something? So y prime is 1 over 2 square root of something times derivative of inside, which is 2x. That's it, you're done. Okay? Now we could also, write this as x squared plus 9 to the 1/2 power and then take derivative with the power rule, but that's more tedious to do. If you memorize this idea that derivative of a square root of something, let me do it here. So derivative of square root of x is what? Is derivative of x to 1/2, which is 1/2 x to 1/2 minus 1, which is 1/2 x to negative 1/2, right? 1/2 minus 1 is negative 1/2, which is 1 over, and we move this to the denominator, becomes 1/2. So it's 1 over 2 square root of x, right? So that's a good thing to memorize. So the derivative of square root of something is 1 over 2 square root of something. And of course, if it's something, that something is not x, then you have to multiply by derivative of inside. Okay? That makes sense? So chain rule is easier if you think of it that way. So think of derivative of square root of a happy face is what? Is 1 over 2 square root of a happy face, right, times happy face prime, right? It's easier to think of it that way. All right, so the answer is this right here. And again, stop the video and see if that makes sense to you. You don't have to separate the functions into u and y. The reason I did that here is to understand that we are talking about what? We are talking about composite functions here. All right, so what's the that? Again, I'm going to think of it this way. What's the derivative of sine something? Cosine something, right? What's the derivative of sine something? Cosine something times derivative of inside. What's the derivative of 1/4 times x? 1/4, that's it. Again, stop the video and see if that makes sense to you, directly going from here to here. Here's another one. Now again, what's the derivative of something to the negative 2? Well, it would be negative 2, right? Derivative of something to negative 2 is the power rule, is negative 2, something to negative 2 minus 1, right? Times derivative of something, right? And that something triangle here is 5 minus 2x. So here you go. Again, you don't have to go through, all this. You just do what I just did, right? So what's the derivative of that? Derivative of that would be negative 2 times 5 minus 2x to negative 2 minus 1 times, what's the derivative of inside? Negative 2, right? So negative 2 times negative 2 is 4. So y prime is 4 times what? Times this, which is negative 3. And negative 3, you move it to the denominator. It becomes what? It becomes positive 3, right? All right. So what if you have 3 functions? So what's the derivative of h of f of g of, it doesn't matter how many you have. See, let's say, what's the derivative of a of b of c of d of e of x? How many parentheses? 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 5, 2, 3, 4, 5, right? What's the derivative of all that, right? What's the derivative of that? Well, the derivative of that would be, so derivative of that would be a prime of all that, right? Which is b of c of d of e of, right? And then 1, 2, 3, 4, 1, 2, 3, 4, 2, 3, 4, like that, times what? Times b prime, so let me not put parentheses here, so b prime of, right, again, c of d of e of x, right, 1, 2, 3, something like that, and then multiply by what again? C prime of d of e of, right, and then times what? Times d prime of e of x times e prime of x, right? So that's why it's called chain rule, right? It's like a chain. So it doesn't matter how many of these we have, we can use the same formula, you see? So if we have h of f of g, it says the answer would be h prime of all of that times f prime of all of that times the derivative of inside. So here is, the chain rule. So you start with the outer function. So the outer function is something to the 5th power, right? So what's the derivative of something to the 5th power? Well, that would be 5 times what? It would be 5 times something to the 4th power, right? So that's the first part. Then times, now you're done with that. Go to the next one. So we got a function here. What's the derivative of this? Well, the derivative of this would be derivative of this plus derivative of 3. Now, derivative of 3 is 0, so we can just ignore that. But what's the derivative of this? Again, this is another chain rule. What's the derivative of something to the 3rd power? It would be 3 times something to the 2nd power. Okay, so we're done with that. And then we go inside here. This by itself is a function, right? And that has a derivative. What's the derivative of that? It's negative 9x squared, right? So, and then you simplify it, of course. But again, the idea is to understand the structure of the chain rule. As I said, 21st century, we do all this with procedural stuff with computers. For last 20 years, there are even calculators can do this for you algebraically. All right? All right, so what about this one? Again, we're going to think of this as what? Cosine of something. What's the derivative of cosine something? Well, it would be negative sine something, right? So the derivative of cosine something is negative sine something times something prime. Now, we don't know what g is, so we just have to put g prime here, right? All right. Again, stop the video if you want to make sure you get this and then continue. So example, let h of x be that right there. If g of 1 is that, and g prime of 1 is that, and f prime of 4 is that, find h prime of 1. Now before we find h prime of 1, find h prime of x. So h prime of x would be, the outside function is f, so it would be f prime of something times what? Something prime. That's it, we're done. Now, we didn't want that, we wanted h prime of 1, so we just substitute 1 in here. And we are given the values of those, right? And we just substitute those values in there. Again, stop the video and make sure this makes sense, right? So we start with this. What's g prime of 1? Is 3. So that's 3. And what is g prime? What is g of 1? Well, g of 1 is 4. So that's 4. What's f prime of 4? Well, f prime of 4 is 7. All right? All right, so I'm going to stop here and then do another video for the next section, okay? All right, so we're going to, I'm going to go over here, and the sun actually set already, almost in my room. So I'm going to see you in the next video, okay? Take care of yourself and others. See you in the next video.